Okay, so we've talked now about the carbon, nitrogen, phosphorus cycles. We've talked a little bit about nutrient pollution, kind of how we interfere in those cycles. So for nitrogen and phosphorus, fertilizers and their introduction to the aquatic environment via runoff is a major source, but also wastewater. So in wastewater influent, we have a lot of ammonia from our waste, and a wastewater treatment plant can convert some of that ammonia into nitrate and then discharge it. And then it can also convert some of that nitrate into nitrogen gas. So again, the conversion of ammonia in the influent to nitrate is nitrification. And then if we still don't want the nitrate going into the environment, we can put it in the atmosphere via denitrification, which can also occur in the wastewater treatment plant. But if we don't fully treat it, we can be discharging that to the aquatic environment as well. So one of the consequences of this is something we call eutrophication. Discharge of nutrients into waterways can cause eutrophication. Eutrophication refers to an excess of nutrients. And so the term eutrophication really technically just means too many nutrients. Eutrophic water bodies are those that have more nutrients than they need. But often eutrophication is also used to refer to all the consequences of excess nutrients. So what typically can happen is too much algae can grow, excess algae growth, which once there's too much algae, the algae at the top of the water column can block light getting to the lower part of the water column, and some of the algae down there can't survive and starts dying off. So we get these large algae die-offs. When they die, we have a lot of organic material that needs to be degraded, and so bacteria go to work doing that. That algae actually creates a large organic loading of BOD, and so as the bacteria degrade that BOD, the dissolved oxygen level can crash, and then we can have widespread death of aquatic life. So fish kills can occur because of eutrophication. But there can be lots of other potential consequences as well, including food chain effects that are more subtle. So some different food sources for fish and zooplankton can be affected at different rates by the different changes in nutrients, and thus, for example, diatoms, which are a kind of phytoplankton that's very nutritious, can suffer when there's too much nitrogen, and they don't grow as well, and thus we have lower quality food sources for fish available. Fish don't grow as large then. They don't have as much reproductive success or numbers. So that's one potential consequence. Another is clogging of water intakes. Surface water intakes, which pump water out into water treatment plants, for example, can get clogged by the excess algae in the water. Taste and odor issues. This is a big one with algae blooms in the East Bay. There's a place called Contra Costa Water District that provides water to a lot of people in the East San Francisco Bay region. And if there's algae blooms in the delta that they take water from, their customers start calling them with complaints about the taste and odor of their drinking water. These come from a couple different kinds of substances. One's called Hib and one's called geosmin. These are harmless chemicals, but they're produced by algae, and they're very easy to taste and smell. And so customers will let you know when they detect those. There can be recreational impacts. So it's not as fun to swim in a lake or a pond that's full of algae. Also, boating can be affected if there's too much of that. Cyanobacteria is a type of algae that tends to thrive when there's a lot of nutrients, a lot of nitrogen. And one particular kind of cyanobacteria, Microcystis, creates a toxin called microcystin, which can cause health effects in people. It can cause rashes. It can cause mortality. It can be poisonous to humans as well as animals. There's been cases in Oregon of dogs drinking water where cyanobacteria had been growing in that water, and the dogs dying. There's been cases in the last few years in the city of Toledo's drinking water supply was shut off for a couple of days when they detected microcystin in water from Lake Erie, and other events like it that have happened. There's one from the city of Salem just a couple of years ago when there were algae blooms in Detroit Lake that resulted in cyanobacteria and microcystins eventually reaching Salem's water supply as well. So all of those things can happen. One thing to note is this concept of a limiting nutrient. So algae need both nitrogen and phosphorus to grow. And if they have a ton of nitrogen but no phosphorus, they can't grow because they need both. If they have a ton of phosphorus but no nitrogen, they can't grow because they need both. And so you could have a case where if phosphorus is your limiting nutrient, for example, you could continually add nitrogen to the water and not really see an impact on algae growth, because unless you add phosphorus, what's limiting their growth is the phosphorus, and vice versa. So you could have environments where the limiting nutrient could be N or P. Typically, freshwater environments are P limited, and so this was the case when people were discharging, or when wastewater treatment plants were discharging phosphates that were in detergents that people were using to wash their clothes. You saw this increased phosphorus level really have a big impact on these freshwater environments, where you'd see eutrophication happen because of this excess phosphorus, because they were phosphorus limited. And then oceans are usually N limited, nitrogen limited. And again, this kind of all goes back to bacteria need nitrogen and phosphorus. There's something called the Redfield ratio. And this is this observation that was made that if I look at the ratio of carbon to nitrogen to phosphorus in most phytoplankton, algae, most environments, that ratio is about 106 to 16 to 1. And the most important part of that is this 16 to 1 part, the N to P ratio. What this means is if you have, again, so bacteria and algae are going to take up nitrogen and phosphorus in a ratio of 16 to 1. And so if your ratio of nitrogen and phosphorus is 20 to 1, for example, then you would say you're phosphorus limited. You have more nitrogen than you really need. Versus if your N to P ratio was, say, 12 to 1, then you might say you're nitrogen limited. You're less than the Redfield ratio. And thus, as you add more nitrogen, you would see an impact, but not necessarily phosphorus. So this gives us an idea of what the limiting nutrient might be. And again, that 106 to 16 to 1 is the makeup of most phytoplankton in most environments. So what can we do about all this? Well, we can obviously prevent nutrients from entering the aquatic environment. One of those ways is to improve our wastewater treatment. So again, we said nitrification converts ammonia to nitrate. We can then add denitrification to our plants and convert nitrate to nitrogen gas. Most wastewater treatment plants in the U.S. do not have denitrification. Most have some form of nitrification going on. Nitrification will happen somewhat automatically when you're aerating water, which you need to do in order to break down the BOD, right? Because as the bacteria in the wastewater treatment plant start breaking down all the BOD, they need oxygen to do that. They consume oxygen. And so you have to provide that to them, and when you do that, you get some nitrification for free. So you get some conversion of ammonia to nitrate. Nowadays, in more sensitive environments in California and Florida, other places, denitrification is becoming more common, but it's still the majority in the U.S. just convert to nitrate and then discharge that nitrate. You could have chemical or biological phosphorus removal. Usually, again, most treatment facilities in the U.S. do not practice any kind of phosphorus removal. The ones that do typically use chemical phosphorus removal, so you're going to add something to precipitate the phosphates out. There are biological methods to remove it as well. Again, kind of rare, but becoming more common. But then also from fertilizers and runoff, how do we prevent that? Well, from stormwater treatment, this runoff issue, we could treat our runoff, our stormwater runoff, before it reaches a water body, and that's what you see in a lot of these low impact development approaches that now developers are being required to include in new developments like rain gardens or swales, green roofs. Better fertilizer management, having plans in place to only apply as much as needed in agricultural areas. That's always been a common thing because people don't want to be wasting fertilizer. Farmers don't want to spend money on fertilizer that they're not getting any benefit from. So they've always, to some extent, watched how much fertilizer they apply, but they also definitely don't want to apply too little and have less yield than they could. And so managing that, predicting exactly what the plants are going to need, and then applying only that much, also adding physical buffers and other kinds of things into the agricultural environment to prevent runoff to surface water bodies is also becoming more common. There's other kinds of state-of-the-art technologies like fertigation, smart fertigation, where just like with smart irrigation, where the plants will only be watered when they need the water. You could mix the fertilizer in with that water at certain amounts. That's all kind of monitored by a central monitoring system, so that you're only delivering fertilizer as needed when it's needed, and not kind of broadcasted where it could run off. And so that concludes the lecture on nutrients. I'm going to also try to find a couple of videos to post from outside sources that I'd like you to watch as well. And that's all.